Okay. Yeah. So, like I was saying, that the reason we can have this two complementary approach to the any biological problem, and in this case, the physics of cancer, is that we can take advantage of the benefits of the both worlds. For example, I mean, from a physics point of view, we can ask the question that can we find the rules or the laws of this biological event by doing some physical measurement. And physicists have been very good in doing that. They could look into very complex phenomena, simplify it, and then find out some of the governing laws, which are not very complicated. On the other hand, as a biologist, you can be interested in the diversity. You can be interested in the molecular details, okay? And you can ask this question: what is the molecular mechanism that decides these rules or laws? Okay. So in this case, your picture will look like something like this: that you have one molecule and then another molecule binds to it, that triggers a signal, that triggers another signal. Eventually, something goes to the nucleus and something happens. Okay. So this is the detailed molecular picture that biologists are going to give you. And at some point of time, they are also going to give you the detail of each of these factors, the structural details of these factors. So if you have the understanding at scale from the generalized understanding from the physical point of view and a detailed understanding from a biological point of view, then you are going to get an integrative understanding of the process. And this is the reason physics of cancer, understanding the physics of cancer is important. Okay, so that you are understanding this process of oncogenesis or cancer formation from the both world. You are trying to understand what kind of rules these cells are following, what is really going on there, and also the moment you understand the rules, you can also start asking the question: what is happening at the molecular level? Because when you are designing a drug, when you are actually thinking about, let's say, killing the cancer or stopping the cancer progression, you have to come to the molecular level and see that what molecular players are important so that you can design a drug targeting that. Okay. So talking about the forces, so what kind of forces in biology we are talking about? So here, what you see here are few cells. So for example, here is one cell which is roughly polygonal, connected to another cell which is also roughly polygonal. And all these white marks, they are basically marking the boundary of the cells. And at this boundary, we can imagine that there can be two kinds of forces. One force is a normal force, another force is a shear force. Let me explain you what I mean by the normal force and the shear force. So from our very basic idea of physics, so the normal forces are when you apply, let's say, a pressure or tension onto something very roughly, when you are compressing something or you are pulling something, the forces that you are applying are the normal forces. On the other hand, if you take an object and you sort of do and slide in motion onto it, and then you are shearing, so you have the shear forces. Okay. So at these interfaces, these normal forces or shear forces are operating. How? Because at this interface, there are these molecules called cadherines or just called cell adhesion molecules, which are connected straight to each other like this. For example, cell adhesion molecule from one cell is connecting to the cell adhesion molecule to the other cell. Now, there are two scenarios that can happen. One, these molecules can fly across each other, like the molecule here is trying to go in this direction, the molecule is trying to go in this direction, which will generate the shear stress. And also what can happen is that this cell is trying to pull this way and this cell is trying to pull this way. This will generate the normal forces. And these are the sort of the forces that are operating in a typical epithelial. It operates at the cell-cell junction level, like I showed you. It can also operate at the between the cell and the extracellular matrix. Now, there is another important mechanical factor, which is the tissue stiffness. So it really matters for these cells whether this part of the tissue where they are taking the support. So these epithelial cells are taking support from this extracellular matrix. Whether this part of the tissue is really soft or hard. Okay, and it really matters for the physiology of these cells. And this is something we are going to see that And in our group, we have explored it to a certain extent, and we have found that it has very, very significant consequence for the cancer. Now, how do you measure the stiffness of the tissue? So let's say if you imagine that there is a cellular matrix stretches very far and its layers are very thin, then you can ignore this as either a stream of the cells over here, or even if you are incorporating the cells into like a cellular matrix, like if you are considering this, then it's actually not going to tarnish your measurement by that much. Okay, so you are just taking the tissue as a material block, like I can take a biopsy punch of the skin tissue from any part of my skin, and then what I can do, I can take something like a cantilever or so and press down upon this tissue, and in the cantilever, if I keep the force level constant, and if the tissue deforms too much, then I know the tissue is soft, and if the tissue doesn't deform too much, then I know the tissue is hard. This is like a very simple way of measuring the tissue stiffness. Another thing that you can do, you can sort of take the tissue, you clamp it, like you can clamp it to two posts, and then you can try to stretch it. By applying the same force, if you can stretch it very, if you can stretch it more, you know that you are looking at a soft tissue. And if you can stretch it very less, then you know you are looking at a stiffer tissue. Okay. So this is how the tissue stiffness is measured. It is just the mechanical response of the tissue with respect to the applied force. Okay. And with this a tissue can be soft and a tissue can be hard. Then you may ask me, what is exactly soft tissue and what is exactly hard tissue? What kind of thing what is soft and what is hard? Okay. So for that, let me give you on the range of the stiffness that we observe in our body. Okay. So we start with this our brain tissue, which is very, very soft, and can be many orders of magnitude harder when it comes to the bone. Okay, and between you have all the tissues. Okay, so what experiment one can do is you can take this some sample from brain, some sample from lung, some sample from let's say cartilage, some sample from bone, and then do the same experiment like with the same force. You press on it, and you see that how it is responding. Are you pressing it? Is it getting deformed? Is it undergoing deformation, or it is undergoing a small deformation? And if you know the force, and if you know that how much you are deforming, you can calculate something called the elastic modulus, whose unit is Pascal. So, in terms of the tissue stiffness, our brain tissue has the stiffness around 50 to 200. This is 50 to 200 Pascal, and our bone will have stiffness in the range of the 2 to 4 gigapascal, which is basically as tough as a glass. Okay, so this is the range of the stiffness we are talking about, and for cell it matters. For example, let's say if you take a cell from lung, and if you are trying to grow at a stiffness value something like this, you are not going to get the lung physiology. On the other hand, if you take a cell from the bone and you are trying to grow in a very soft tissue, you are not going to see the behavior of the bone cell, there. So this stiffness range, which is a mechanical property of the tissue, matters. Okay. So with this thing, one of the question is how do you? I talked about sort of the forces between the cell and the forces between the cell and this extracellular matrix. So one of the question is how do you measure it? Okay, how do you measure such things? Because in order to do experiment, so either you have to measure or you have to plot. So the first thing, for the quantification, what you can do, you can sort of have many chemical inhibitors, which will sort of mess the intracellular machinery. So the first generation will stop. But the tougher question is how do you? Yeah. Sorry. Oh, okay. So I'll stay here. Okay, all right. No problem. Yeah. So, so the thing is, how are you going to measure the forces between the cell and this extracellular matrix? So one of the ways we do it in the lab is by using a technique called the traction force microscopy. So what happens in the traction force microscopy? In traction force microscopy, you grow the cells. Let's say these cells are like 10 micrometer, 20 micrometer diameter. Let's say the width of your hair. And these cells are cultured over a substrate which is compliant, polyacrylamide gel, some sort of gel. Okay? And in this gel, we have this fluorescent marker beads over there. So when the cell is applying forces on the substrate, they are deforming the gel. Now, if you know where the undeformed positions of these marker beads are, and if you know where they are getting displaced after the deformation, from these two information, you can actually calculate the forces. So for that, what you have to do, you have to take the image when the cells are not deforming the substrate, and an image where cells are there and they're doing something, and as a result of that, they are deforming the substrate. So the moment they deform the substrate, the cells will get from their sort of relaxed state, so relaxed position. So you take the two images, you take this image, you take this image, and then if you compare that how the beads are getting displaced, so from there, from this displacement, you can calculate the forces. So this is just to give you an idea. This is how we measure forces. We can measure forces that the cells are exerting on the extracellular matrix. And we know that in terms of these forces, on the softer surface, cells are able to generate lower forces than on the stiffer surface. Okay? So this is some of the thing that you should know about the physics of cancer on the physics side. That the main forces that we are talking about are the normal forces and the shear forces. The tissue stiffness or the stiffness of the extracellular matrix is a very key parameter. And there are techniques, of course, this is not the only technique. In our lab itself, we use multiple techniques. There are many techniques with which we can measure these forces. Now, with this introduction to the physics part, the force part, let me come to the next part, which is a cancer. And what I'm going to do, I'm going to give you a very simple delineation of what happens in cancer. Okay? So in cancer, what happens over here? Somehow the abnormal growth of cells starts in an epithelial tissue. Since we are talking about the cancer of the epithelial tissue, which are anyway 80% of the cancer incidence. Okay? So somehow we do not know, we do not care at this point that how these growths are starting. There may be some sort of mutation. That mutation can come from any sources. It can come from UV, it can come from tobacco, it can come from multiple injuries, it can come from the errors in cell division and replication. It can come from anywhere. We do not care. It just so happens that there are some cells which becomes abnormal and they start proliferating and they sort of disobey all the tissue architecture we are seeing. So for example, if I go back, you see this epithelial cells have a very nice arrangement. They are not climbing onto each other. Okay? So the cancer cells do not have that respect. So they are going to pile up, they are going to amplify the number, and eventually they are giving rise to the what we call the primary tumor. Now, having primary tumor is not a big deal. In fact, very few people die of the primary tumor, except when it forms in the brain. The problem what happens is that since the cancer cells proliferate and they occupy a very limited space, very slowly they will start running out of their food supply, their oxygen supply. Okay, so for that they have a nice little trick with which they will attract these cells which form the blood vessel, what we call the endothelial cell, to these cancer cells. Okay, and then this blood vessel will sort of form a new. This endothelial cell will form new blood vessel over this primary tissue. And do you know why cancer is called cancer? Anybody? Why does it look like a cramp? Yeah, partially correct. So the thing is, the reason when they sort of 200, 300 years ago, when they started taking out these tumor from the body, they realized that their tissues are like solid bone, and which is covered by these blood vessels, red blood vessel, which look like a crab spreading its claws. Okay, and this is the reason cancer is called cancer. There is no other reason. Okay, and this, as you understand, this vascularization, creating a new blood vessel over the cancer tissue is absolutely important because of two reasons. First of all, the cancer cells are getting their nutrient supply, they are getting their oxygen, and the second thing, the moment it is connected, they are getting the access to the highways of the body. And the highways of the body are blood vessels. The reason one thing can spread from the one part of my body to another part of body very quickly, because we have these highways for the blood vessel. And the moment the cancer, this blood vessel comes to the cancer tissue, or the primary tissues, the cancer cells in the primary tissue, they have the access to this highways of the body. And then what happens, some of them will detach from this primary tissue and primary tumor, and then they will migrate, and then they will come to this blood vessel. They will make a hole between this endothelial cells which form the blood vessel. They will in fact squeeze between two endothelial cells, and then they are entering the bloodstream. And once they are entering the bloodstream, this is where all the problem begins. Because now this primary is the cancer cell, which was otherwise restricted to the primary tumor, can now spread all over the body and colonize into different parts of the body. Okay, so the cells basically take this blood vessel, they flow with the blood, and they will time to time attach to some remote part of the other tissue, and again they will sort of make switch is in between these endothelial cells and come out of this blood vessel and start colonizing as a new site. And this is the phase which is the dangerous. This is what we call the stage 3, stage 4 of cancer, where you start seeing the cancer incidences of a lot of position in the body. And most of the time, this is the stage where the game is over. Okay. If it is primary tumor, then you have an option of killing the cells locally. You also have the options of removing them surgically. But the moment they have undergone all these things and they have started colonizing the other part of the body, is mostly we cannot do anything. Okay. So with respect to this process, the forces operate at the different phases of the cancer spread. Okay. So first stage is that when these cancer cells are growing in the primary tumor, you imagine that the tumor has a really, the primary tissue has a really constant pace. So there is nothing called unlimited space in our body, right? And these cells are all of a sudden, they are basically breaking that structure, the systematic structure of the epithelial cells. They are proliferating and filling up that gap. And because of that they will start sort of pushing out the surrounding tissue or the normal cell or the healthy cell or even the extracellular matrix. So that will create some sort of what we call the solid stress. Okay. So then once the cells are taken, the highways of the blood vessel, so then they are exposed to the fluid stress. How? So let's say if you're trying to swim in a river, of course you will encounter some sort of fluid stress, right? So this fluid stress will be generated because you have some relative motion between you and the fluid. So because of that, you are going to have the drag force, you are going to have the shear force, which is of the fluid mechanical origin. And the third thing is the stiffness that I was already talking about. The cancer cell can squeeze through a softer tissue, but they may find it little harder to squeeze through a stiffer tissue. And then eventually, these cells, like I was telling you, they had to squeeze between the cells, between endothelial cells, right? So for this, they had to undergo some kind of massive structural changes within their body. And as a result of that, they experience a lot of forces. So it is like, let's say there is a crowd and you're trying to squeeze in between them. So you are going to sort of push the crowd a bit, and crowd is also going to give some force on you. So you are going to experience some forces. So the forces operate at different levels of the cancer progression, and all of this thing matters. Okay. So for sake of simplicity and for sake of time, I'll be restricted to the one kind of situation and one kind of mechanical cue here, and I'll give you an example which is most important and which is sort of under clinical trial. So that takes me to sort of 4,700 years ago. Okay, the picture that you see is one of the, let's say, the erudite person of the human history, and so he was a priest, an astronomer, a prime minister. He had many titles, and his name was Imhotep. So you may know the name Imhotep from this movie, ironically, who is a villain. But believe me, the Imhotep was not like anybody like him. Okay, so Imhotep was somebody who was very erudite person. And what Imhotep did in 27th century BC, he studied the disease very categorically. Okay, so he had written a papyrus where there are at least 50 diseases which he gives very good description. So what he does for each of these diseases, he describes what are the symptoms are, and he then describes what the treatments are. Now, in a modern standard, those treatments may sound very funny. For example, if a person has some sort of problem, and he is prescribing that that person should be bathed in elephant's milk or something like that. Okay, but at least he was suggesting a cure to all of his diseases, except there is a special case, which is the case 46. In this case, he is describing that a woman with bulging lumps in her breast that feel like an unripened fruit. And when it comes to the cure portion of this specific case, Imhotep just offers one line saying that there is no cure. Okay, and he writes that not even a magic potion will do. So according to the recorded history, this is the earliest case of a breast cancer, and see that how it is being detected. It is being detected as an unripened, and what you can imagine as a solid tumor. Okay, so even in 4,700 years ago, a person detecting cancer by using some physical property, which is the stiffness of the tissue. Now it took us, and doctors also have been using this time to time. Before they would do the biopsy, before they would do some kind of medical test, they would actually feel the tissue to see something normal or abnormal. And when they say normal and abnormal, they are basically talking about the differences in the elasticity of the tissue. Okay, because they are trying to feel it. And it took us 4,700 years almost to do actual experiment where people are bothered to measure the stiffness of a normal mammary epithelium, that is the breast tissue, and when the tumor and a breast tissue with the tumor. And it turns out that the normal mammary gland has an elastic modulus of 167, it's a 200, rough number, 200 Pascal, while an average tumor will have something like in the 4 kilopascal. So we are talking about 20-25 times increase in the tissue stiffness. And what these people did in 2005, they cultured this mammary cells or the breast cells, and when they cultured over a softer matrix, a softer extracellular matrix, which mimics a normal mammary, they form this sort of very nice epithelial tissue, in the sense they form this hole-like structure where the milk will eventually get secreted. Okay, but as you increase the stiffness of the extracellular matrix, you start producing a tissue which looks very unlike what you see over here. Okay, it doesn't have this architecture, it doesn't have this hole, and there are cells which look like extended and they are ready to migrate. And that is exactly the morphology of a cancer cell which is migrating out of the tumor tissue. So the thing is, yes, the tissue stiffness matters in breast cancer, and later it was found that the tissue stiffness matters in many cancers. And what happens is that, if I can sort of tell you in a story-like manner, that as the cancer progresses, the tissue stiffens. And the stiffening of the tissue then instructs the cancer cells to grow fast. So this is forms a very vicious cycle where the cancer cells are instructing the tissue to become stiffer and stiffer, and the stiffer tissue and then instructing the cancer cells to grow more and more. Okay, and this is where we have a massive problem, not in the breast cancer, not only in the breast cancer, but in many cancer. Now you may ask that why do the tissue stiffen? How are the cells, cancer cells, making the stiffer tissue? So to this, I have to take a travel to a little bit of the molecular biology. Just bear with me. So again, I'm talking about, let's say that you imagine the cancer cells are forming over here, and this is the extracellular matrix we are talking about. The extracellular matrix like this, like I told you, it is made of a protein called collagen. Now you can imagine the collagen just like a string-like matrix. So there are a lot of strings which are connected to each other, okay? And together they kind of make a structure with some sort of elasticity, with some sort of mechanical rigidity. Now, if I tell you that if you take two structures where the strings are very loose and not connected to each other, and in another case, these strings there are many such strings, and they are really connected to each other, which will be sort of a stiffer. Any answer? The one where all the strings are connected to each other, right? So this is precisely what cancer cell does, okay? So in a cell, there is a protein called lysyl oxidase, which will do some chemical reaction, which I do not want to go into the detail, which will connect this neighboring string as such. And what cancer cell does, they produce this lysyl oxidase protein more than what is required for a normal tissue. And as a result of that, the tissue will have this extracellular matrix, will have more and more cross-link, and as a result of that, there will be stiffer. And rest of the story, I already told you that the stiffer matrix will tell the cancer cell to grow faster, and you will have this very vicious cycle run. Okay? Now the question is, I showed you that this discovery was made in 2005, which was 17 years ago. Okay? So what has been going on? So if we know that the tissue stiffness or the stiffness of the cellular matrix is a very important parameter, and it is promoting cancer formation, this process of oncogenesis, is there an approach to sort of stop that? Okay, so of course there are ways to do it, and now the drug companies, they are sort of doing the trial of many compounds which target this problem. One of the things that you can think about is to just stop the activity of this lysyl oxidase. Of course, this is going to have an effect on other tissues as well, because the lysyl oxidase will be needed for other tissue in some quantity, but at least it will stop cancer cell using this lysyl oxidase to cross-link the collagen. Okay? And also, there are basically two drugs, which is one GF6624, another is TIFR-Hyderabad, which is undergoing this drug trial for many cancer incidences, and there are some positive indications that they may work. Another thing is that when I talk about this extracellular matrix and the cells, so the cells and extracellular matrix are connected via some molecules. Okay. Till now, I have been just drawing a cartoon, just a line to sort of connect the cells to the extracellular matrix. But in practice, they are made of molecules called integrins. So what if you just decouple the integrin? If you decouple the cells from this tissue, okay, by blocking this integrin, then although your tissue may stiffen, the cancer cells are not percepting it. And because of that, I told you that there is this vicious cycle, that the cancer cells stiffen the extracellular matrix, and the extracellular matrix tells the cancer cells stiffen extracellular matrix asks the cancer cell to grow more. So what if you block this? So in this case, in the top two cases, you are blocking this one, this part, where the cancer cells were stiffening the extracellular matrix. But you can also block this part, where the stiffened matrix is actually interacting with the cancer cells. So if you do that, you can do that by blocking this integrin molecule. And there are drugs like the humanized monoclonal antibody like this BG0011ST. Yes, I mean, this is the trade name, and this is the code name. So this has been trial for the lung fibrosis and some of the cancer instances. So the point to be taken over here, this extracellular matrix and especially the stiffening of it plays an important role in cancer progression. And it is a part and parcel of the cancer progression. And indeed, there are approaches now taken in with which people are trying to come up with the small molecules, inhibitor, monoclonal antibodies to stop this process. Okay, and because it is sort of inhibiting the mechanical interaction of the cancer cell to the extracellular matrix, this can be clubbed under a field called the mechanomedicine. Okay, so for now, 1 decade, we actually have a field called mechanomedicine, where the mechanics of the tissue to sort of given an emphasis. With this introduction, let me come to the last one. And this is where I'm going to talk about what we are doing in this respect, that the physics of why I'm talking about physics of cancer and what we have done with or we have done or what we are doing with respect to the physics of cancer. So one of the things, and before I do that, so all the work that I show are either done by Shilpa or Prabhat or in collaboration. Okay, so they are the main player. I sit in the office, they do the experiment. So if you have more query about the experiment, how it works, how challenging it is, how difficult it is, please talk to them. So the thing that we are working in, so till now what I was talking about is the cancer progression. That you have a primary tumor, the primary tumor is growing, and then it is progressing. Okay, but you have to remember that the cancer causing mutations are surprisingly common. Okay, so every minute in our body there are estimated 40 cells we are producing in 4,000 cells, not 40 cells, 4,000 cells, which are mutated. And if you imagine that even 1% of these cells are transformed or potentially cancer, okay, then every minute in your body you are producing 40 to 50 potential cancer cells. And if you think about that, and if you are accumulating so many of cancer cells every minute, then we would not go to an advanced stage ever. I mean, we will all have tumor and we will all die of cancer in very early age. But the reason that doesn't happen because our tissue itself has a quality control mechanism. Apparently, when a cell sort of gets transformed by this mutation, the cell surrounding this mutant cell has a way to detect these cells. Okay, and what they do, they realize that this red guy is not like them, and then they trigger something to get this red cell out of the tissue. Eventually, this red cell will die, this mutant cell or potentially oncogenic cells will die, and our immune system will take care of the debris and so. And this so-called blue cells or the healthy cells or the wild type cells, they will proliferate or divide to fill this gap. This is the quality control mechanism or the cell competition, or there is a nice name, epithelial defense against cancer. So the cancer is a disease of the epithelial tissue. So the epithelial tissue, to remain healthy, it has to mount a defense against cancer. Okay. So this process has a nice name called epithelial defense against cancer. And this is the reason we do not develop cancer at early stage of our life. Only when this process fails, you have the primary tumor. Okay. So what we're trying to understand here is that how this healthy cell detect that their neighbor has gone bad. Okay. So, yeah, so for this, the question that we are asking that what do the cells sense? How do the cells sense that there is a red cell, there is this bad cell which is next to it? Is there a mechanical cue? Is there a chemical cue? Are they sensing something? And the question is, how do the physical forces or the mechanical cues, like from the extracellular matrix, like we are talking about the stiffened tissue, stiff tissue and the soft tissue, affect this process? Now there is a problem. The problem is when you need to study this, you stumble upon a problem of randomness. Because in our body, this 40 or 50 cells, whatever per minute, they are all operating randomly and they are getting sort of generated all across the body, right? So you do not have a very good way to follow a cell from the mutation to see that how it is interacting with this neighboring cell and what is happening. That is impossible to do in our. But what if we create a model where we can create a generate a cancer cell at our will and then watch that how surrounding cells are reacting to it. Okay. So this is the model that we have in our lab, where you see this, first you look into this image, you'll see this entire field of view is filled with cells. And then you see this part of the frame where you see that some cells are marked green and some cells are dark because they are not having fluorescence. Okay. So these green cells are potentially cancerous. So they are bearing a cancer-causing mutation. And this dark cell, which is not carrying any fluorescence, are our healthy white type normal cells. Now, what is happening over here? These green cells, as you see, the greenness is increasing over the time, right? So, in the beginning, if these cells will not have any green at all, because we have, so this protein that they are expressing, which will mark them to be cancerous, is not always produced in the cell. It is produced only when we want it. Now, how might we do it? This is where we have to go a little bit of molecular biology and think about the central dogma, how from the DNA, RNA is produced, and from the RNA, the proteins are translated. So, if you stop something at this level, you stop something, production of the protein, although in the gene, you have that signature, you have the gene to produce this protein, but if you stop this process, then this protein will not be produced, right? Suppose you have a switch, some kind of chemical switch, but by which you can on and off. And most of the time, you can keep this switch off, so that even if the gene is there, this HRAS V12, what you see, which is the cancer-causing gene, the protein is not getting produced. And if the protein is not getting produced, cell will not have any problem. And then suddenly you turn on the switch. The moment you turn on the switch, this protein is getting produced, and this protein is marked with the green fluorescent protein, and that's why we see this cell as green. Okay, so we can actually trigger the exact moment when a tumor initiates or the cancer initiates, and then we see that how our neighboring cells are reacting to it. And with this, what you can see, if you look at it, that it is the two-dimensional projection, but if you look into this plane and this plane, you realize they are popping out. These cells, these cancer-causing cells, they are popping out. So exactly the process I was describing, they are being kicked out of the tissue. Okay. So one of the questions that Shilpa asked, given this model, is that how the stiffness of the tissue affects this process. Now you may ask that where is the stiffness of the tissue coming over here? Okay, because I told you it's the cancer cell which make the tissue stiffen, and here the cancer cells are just getting produced. I mean, they probably do not have the time to make the tissue stiffen. But you have to remember, tissue doesn't stiffen only because of cancer. They stiffen because of multiple reasons, and one of the reasons is the fibrosis. You may have the fibrosis because of the COVID, because apparently very severe infection to the lung, it causes the fibrosis of the lung. Okay, and the people who undergoes injury, let's say because of the alcohol abuse or because of the other reasons, by smoking and so, if a tissue gets injured again and again and again, each time it is doing a local wound healing, and because of that, the tissue undergoes something called fibrosis. The name suggests it is forming a lot of fiber, again of collagen fiber, and the tissue is getting stiff. Now the question is, if you are already predisposed to such a tissue, like stiff tissue, then how does that affect this process? How does that affect this quality control process? And people become interested in this because this fibrotic tissue are the places where most of the time you see the future cancer is emerging. So there's a very high correlation between the tissue fibrosis and the tumor formation. Okay, and nobody knows, there are many possible explanations, but nobody knows for sure that what is the molecular connection. So this is where Shilpa did a very simple experiment. So what she did she performed this cell competition experiment over a soft tissue which mimics an healthy epithelium, extracellular matrix of a healthy epithelium, and then on a stiffer tissue which mimics the extracellular matrix of a fibrotic epithelium. And what we observe is that on the soft ECM, these cells, these mutated cells, got kicked out and eventually they will die. But on the stiffer ECM, stiffer extracellular matrix, they continues to be part of the tissue. So somehow the tissue loses their quality controllability or their defense against cancer if they are already stiffened. Okay. So if you do the statistics, if you have several of these colonies in the experiment, and if you try to find out that at any point of time, how many colonies of these mutated cells are coming out of the tissue, then in a softer matrix within this sort of kilopascal range, 1.24 kilopascal, you will see that 80 to 90% of the cells of these colonies are getting evicted. They are getting driven out of the tissue. In comparison, if you are working with the stiffer tissue or the stiffer matrix, you see only 50% or even less than, and that fraction of these mutated cell colonies are actually coming out of the or being out of the tissue. So that means this result basically suggests that having a predisposed fibrotic tissue biases created the bias in favor of cancer, because it shuts down a very important epithelial defense against cancer. Okay, so this is one of the findings that we published very recently in a journal, and you can go to our lab website, you can access this, and this is freely available. So please go through it if you are interested further, and if you want to know what is happening at the molecular level. Now, yes. Yes. No, so they are pre-designed. So you take a tissue, you take an extracellular matrix, which is soft. You do this experiment. You have another sample where you have a cheap extracellular matrix, and you do this experiment. So these are different samples. So we are not dynamically switching from one. Could you please be a bit loud? Yeah, so this is exactly what we are looking at. So 1.2, 4, 11. So these are all the stiffness of the tissue. Okay, okay, and the drop is drastic. So it is not gradual. So below stiffness cutoff, the cells are getting removed. Above that cutoff, the cells are at least a large fraction of these mutant cells are not getting removed. Okay. Now, coming to the question, is the cancer tissue is stiff? That must be, we know that the cancer cells are making the tissue stiff, and also it is helpful from them in either way. So for their progress, as well as decently the epithelial defense against cancer, right? But are the cancer cells themselves stiffer, or are they soft? Yes.
Small question.
Yeah.
So are you trying to draw a link between that tough and fibrotic tissue with cancer cells which are rapidly multiplying, hence the density is increasing and it's becoming dense and dense, and hence the toughness that is there?
No, so here, like I was saying, this is where we are looking at the epithelial defense against cancer. Okay, so this is before the primary tumors are formed. This is what I'm saying that it is post. So for some reason, because of the repeated injury or some problem, maybe the COVID infection, somehow the tissue has got stiffened. Given the tissue has got stiffened by fibrosis, what is the chance that this tissue will develop the cancer? And the studies tell us that the chance is absolutely very, very high. So there is a very high correlation. Okay. Question is why? And the answer is because the basic epithelial defense against cancer fails on a stiffer tissue. Okay, which is already been stiffened by some other disease or some other problem. Now, the question is, the tissue is stiff, but are the cells stiff? And you may see that the tissue is made up of this extracellular matrix and the cell. But the cell is a little fraction of this entire tissue. The tissue is mostly composed of this extracellular matrix or this collagen, right? So even the cell can be soft, can be stiff. It really doesn't part of the property of the tissue. Is that, like I'm saying, this collagen cross-linking? So this is the property of the extracellular matrix, the collagen, that kind of governs the stiffness of the tissue. And the reason you ask this question, because if the cancer cells themselves also get stiff, then they have a problem. You imagine that these cells eventually have to migrate to the blood vessel. They have to switch through the two endothelial cells. They have to go to the bloodstream. And then when they're colonizing to the new tissue, they have to do it again. So they should have some sort of deformation property by which they can sort of travel to the blood vessel, switch in between two endothelial cells, flow, go with the flow, and then again squeeze back and colonize to a new place. So if your cancer cells themselves are very stiff, probably they won't be able to do it very well. Right? So there is a guess that the cancer, although the tissue itself becomes stiff because of the cross-linking of this protein like collagen, what is called the extracellular matrix, and that is why it is extracellular. It is not the cell which is cell. But the cell themselves may not be stiffer. In fact, they could be softer. So, in this respect, what Tamal has observed is that when he did this cell competition experiment, again we are looking at this mutant cell population or the cancerous cell population surrounded by the so-called normal population. When you look at this nucleus of these two populations and compare them, as you can see within this border, I have this potentially cancer cell. And if I draw the outline of this nuclei, it looks like very deformed. They look like very lobulated as such. They are much more different from a spherical nucleus, okay? On the other hand, if you pay attention to the surrounding healthy cells, you see that their nucleus and their nuclei are more or less spherical. At least they are not like deformed or lobulated like this one. For example, you see that this nucleus are deformed like this one, okay, in a mutated cell, which is not the case if I pay attention to the surrounding cell. So the question is whether this is a discovery, and the question that Provan is asking whether it is consequential. Does it play any role in tumorigenesis, in cancer, or in the epithelial defense against cancer? Okay, and one of the ways it can play a role because nucleus. So this is a very simplistic sort of picture of the cell, where cell is one block which is encasing smaller block called nucleus, and nucleus requires a significant volume within the cell. So that if the nucleus becomes deformable, or in the other word, if this becomes fluffy or loses the rigidity of the nucleus, loses the rigidity. So as a whole, the cell is also going to lose the rigidity. Okay. So imagine that you have a material where you have one material inside which occupies a significant space and contributes to the significant part of the body, and it is encased by another material which is also occupying some part. And your material property is basically the average material property of the inside material and the outside material. And somehow, if you have managed to soften the inside material, on an average, the average material property is going to go down. So, if the nuclei become deformed, they become fluffy. The cells are also going to become fluffy, and on the other way, so they are going to become softer. Okay? So, this is the argument that we can sort of think about it. This may be happening to the cancer cell. So what would be its consequence? So for this, you have to think about a very real life scenario. And this scenario is nothing but wetting a paper with a water droplet. So if you put, let's say, a water droplet on a paper, then locally the paper kind of swells up. Okay. What's the reason it swells up? Because the water droplet will soften the paper wherever you are putting the droplet, and it is surrounded by the relatively dry and stiffer paper. And because there is a mechanical mismatch, the softer paper will swell up. So if you imagine that our nucleate cells with their fluffy nuclei is giving rise to a softer, which is giving rise to a softer part of the tissue, which is surrounded by the stiffer part of the tissue. This is going to act very similar to sort of the weighting of the paper, and it is going to swell up and it is going to bump. And if you compare the analogy between this and this, it is not too far-fetched. Okay. In fact, these mutated cells eventually they will buckle like this, the way sort of I represent over here by couple, and then they are going to get removed from the tissue. Okay. Now, how do you know that? So one of the questions that you ask here, that this is a story. I mean, it has too many things I have said. So our observation was that we had this deformed nuclei, right? Now I am claiming the cells of software, and this is sort of creating this thing, right? And you can challenge me, where is the evidence with which you prove that these cells or this mutated or this cancer population is software? Okay? So this is an experimental challenge, and there is no technique available by which we could measure it. So this is where comes forward very hard work and persistence over 1 year against multiple failures. Okay. So what I'm going to present in a single slide, just believe me, it is almost like 1 year of continuous effort against multiple failure, and multiple I mean in the number of 80, 90 times repeating one experiment. Okay. So what we have invented now, a technique in our lab called the gel technique called gel compression microscopy. So what is happening over here is that we have two gel systems where there is a gel in the middle like this one, which can be swelled if we change the pH. So this gel is swing if we maintain it at a low pH, and if we change the pH to something like a physiological pH, like 7.4, then this gel will swell. And these yellow cells are the gels where we culture our cells. Okay. Now, as you see over here, if this orange gel swell, it is going to sort of press on the cells on top of this yellow gel, right? So, if the orange gel swells over here, and these are the cells on top of this yellow gel. So this orange gel is going to press on the yellow gel. Now this is completely determined by the chemical reaction. So each time the forces applied, or the compression applied by this orange gel will be similar. What we are going to look at that under this same forces, how a normal tissue and a cancerous tissue behave. Okay, and when you look at that, you see a very remarkable different behavior. So here, this is the initial line, the interface between our expandable gel, which is the orange gel, and the yellow gel on top of which we have the cells. Okay, so this is the initial boundary, and after the expansion of the gel, the boundary gets shifted to this white line. So from the yellow line, it gets shifted to the white line because of the compression. And the reason it can be compressed further because the cells are also mounting a resistance because they are elastic. They also have their rigidity. They are also come. Okay? But if you look at this cancerous cell, so our raspberry 12 cell, then you see that the difference is much higher. So that means that here the yellow line is this is the initial position and this is the final position. So if you look at the difference, For the same applied pressure, because of this expandable gel, the difference here is much farther than the difference over here. Okay, and it shows you that these cells are almost 2.3 times to 3 times more compressible than our wild type cells or the normal cells. So this experiment conclusively shows that the cancer cells that at least that we are dealing with, they are actually softer. Okay, and that kind of completes the picture that if these softer cells are surrounded by the stiffer cells, then they are going to be this buckling, and the cells are going to be sort of evicted out of the tissue. So the point that I'm sort of bringing here, that there is not always you have to go back to the molecular details, not always you have to think about this signaling pathway, that signaling pathway. In fact, we are going to go there. In fact, Tamal is also studying that why do these cancers loses the structure of their nuclei, okay? Why their nuclei become fluffy? So this is why we entered the molecular details. The simple physical explanation possibly can offer you that, that something very physical is happening over here, and just a simple mechanical mismatch can have a physiological consequence. Yes, you have a question.
How is the density of the cells because that is an important parameter. If you have one cell versus 100 cells, right? That would give you a very different view.
Yeah, so we try to maintain the density at the same level. For that, you have to seed the cells at some precise time. So we know the doubling rate of the cells. So that studies they have done it already. So if you seed the cells at a precise time, then you are going to end up with the similar density.
But is there a way to measure that?
Yeah, you can. I mean, you can segment all of this. I mean, you take the images. I mean, if you take in a little bit higher magnification image, you can segment it, and that is easy job. Yeah.
Which control the expansion each time you do it? You have exclusive control on this expansion, how much force you're generating.
Yeah, so Prabhu has done some study. So, and also the data I'm talking about comes from many such experiments. So it doesn't vary that. So the weight of the data, I didn't produce the, I'm not putting the distribution of data. Yeah, it doesn't seem to be a factor. Yeah.
Here we are saying that the assumption now is that the cancer tissue is softer, and so it
Cancer cells are softer. Yeah.
Cancer cells are softer, and then it buckles up. But in one of the previous slides, we have said that we have seen that the tougher tissue doesn't eject out the cancer cells, which is a problem. So, but in combination of tougher tissue, and even if the tissue is tougher, if the cells are softer, why doesn't it eject out?
Yeah, so this is the dot. This is a very good question. This is the dot we are trying to connect right now. It has something to do with the adhesions of the cells with the extracellular. That could be a possible explanation. So we do not have and there could be a molecular explanation. So this is something we are exploring right now. Okay. So because you see, for this is so what I say is nuclear deformation. For this, there are a lot of molecular things happening. Okay. So there is a protective cage around the nucleus, which provides that it is getting dissolved. The protective cage is getting dissolved. So it is likely that this protective dissolve of this protective cage doesn't happen over the stiffer tissue because of some connection between the cancer cell and the stiffer tissue already present, which do not allow them to become softer like this. Okay. Yes, we can. So for that, you need to have an atomic force microscope. Yeah, that's a very good question. In fact, people have done this. Okay. Yeah, in fact, people have done this, and the reason is that here, if you look at the thing that we are looking at, that our setup. So this is not a single cell, right? This is the multiple cell. And the multiple cell give rise to a property, it's an emergent property or collective elasticity, which is going to be different from the elasticity at the individual cell. So we are interested in the collective elasticity, that together how much resistance each of these populations, let's say the normal cells and the mutant cells, can offer. Okay, so this is the reason measuring these properties at the individual level will not answer the question that what is happening at the collective level. But that's a brilliant question. Yeah. So this is what I have to really, I mean, if I give a yes or no answer, this will be very, very simple. All I can say is that the mutation, so cancer is a very, I mean, okay, so one disclaimer. So I tried to picture, sort of make a very simple picture of cancer and the physics and everything, right? One thing you should keep in mind is that the cancer is a cohort of multiple diseases. Each cancer has its own property, and so although this tissue stiffness has emerged like an uniform property that happens in many cancers, but each cancer has its own, in biology, what we call the phenotype and its own characteristic. So only thing that I can say, the mutation that we are working with, this HRAS V12, that mutation, this HRAS, so this is an oncogene. So for this specific mutation, for this specific oncogene, this is what the result is. But if you ask me whether you are going to get it from the other oncogene, I do not have an answer until unless we do this experiment. Okay. It has, I mean, so you have to go through this database of the cancer. So it appears in many cancers. I mean, in some lung cancer, some colon cancer, and so. Okay. Yeah.
So on this slide, you're saying you're looking at softness as the hallmark of whether cancer or wild type. So have you thought of a slightly different kind of an experiment where you check the movement or extrusion? That is the first part of the work which Shilpa is working on. So if you have a wound and you have a collection like healthy cells and then a cancer cell, and you kind of use an optical tweezer to see the force that is being exerted to move towards the ceiling or the cell migration. Exactly.
Yeah, so Prabhat has done some experiment, not like the experiment you are suggesting, but very similar to it. So you have the cancer cells migrating, I mean, these are cells migrating, and you have the wild type cell or the normal cells migrating. So apparently, when they meet, these cells will move them towards one side. Okay, so he will have the video. So if you are interested, you can take the videos from him. Okay. What exactly? So yellow dotted line is the initial position of this interface, and the white dotted line is the final position where the interface is. Okay. So this is the initial and this is the final. So this is the difference in case of the normal cell, and this is the difference in case of the cancer cells. Okay. So that brings us to the end of the thing, and I'm just going to say a couple of things. So first of all, so as a biologist, we tend to always tend to think about molecular signaling, right? That this happens, this molecule get activated, then this triggers another molecule, then that triggers another molecules, and so. And we try to elaborate. We try to draw some of these elaborate signaling pathways. I'm not saying that's not important. This is very, very important. In fact, for this presentation, I did not present any of this, but believe me, after we find out this physical behavior, we then become biologists, and then we actually do molecular experiment to find out what happens at the molecular level. So in case of the tissue stiffness story, we found that a protein called filamin, which has some different localization property depending upon which kind of tissues are that. That triggered something, okay? And for this one, for the nucleus, Provo already has some discoveries where he have found that there is a protein called guanidine which forms a cage around the nucleus, which are really down-regulated, and as a result of the nucleus is changing its shape. So the molecular part of this story is interesting. But what you have to realize, and this sort of takes me back to like 100 years ago, what the person called D.R. Thompson was trying to do was to say that molecular story is not always necessary to explain a biological phenomenon. Okay, and what we are demonstrating over here, there is an underlying molecular mechanism. Eventually, all this physical signals has to get converted at the molecular level. There will be changes in the genetic level. There will be changes in the protein level. But if you understand the process at the more phenotypic level, more physical level, then what you offer is a very simple explanation to an apparently complex problem. Okay? And this is precisely what we are trying to do in our group. So we are trying to look at the cancer biology from a physicist point of view to make sense of the otherwise noisy molecular data. So this is exactly what our group is trying to do. And in this thing, I'm just going to quote Sidney Brenner, who said that progress in science depends on new techniques, new discoveries, and new ideas, probably in that order. So in our group, people like Robert, they're trying to always come up with techniques. So if you do not know something, if you see that there is something is missing, you try to come up with a technique which will enable you to measure something, okay? As an experimentalist, you have the burden to measure. You can have 10 hypotheses, that is fine. But eventually, you have to design an experiment which will tell you that which hypothesis is right. And to test that hypothesis, time to time, you have to come up with new techniques or invention. Because if you are working really at the cutting edge of the field, you may not have the techniques available. Maybe nobody has looked into this thing, so the techniques are not available, right? So what we do in our group kind of follow these two philosophies, that we try to devise new techniques which lead to new discoveries and new ideas. And we are trying to understand the cancer biology, and also there is another problem which I don't talk about, which is wound healing, from the point of view of physicists to make sense of the molecular data. So none of this would be possible without the contribution. Like I told you, I sit in the lab. I think last time I did some experiment was 3 years ago. So these are the wonderful people who are doing all these experiments, and they have somehow unintentionally included a dog into it, because most of the time the cells that we are using MTCK cells, which is of the canine origin. So I don't know whether this is unintentionally intentional or what is this. So they are the ones who are doing all this experiment. So take your time to talk to them, because what you get from me is an overall view and some sort of overall lecture. Right? So, but if you have to really know that how these techniques are working and what kind of time they are spending to sort of implement this technique, what challenges they face, then you have no other way but to talk to them. Okay, so there are many strange problems, but eventually we circumvent all of them. And in this process, we offer fantastic collaboration. Mohit Jolly in IIC, Max in the Northeastern, Freedom in Munich, and there are other people we collaborate with. And in house, we are always discussing our work with Manish, Anish, Saroj, and Ullas, and others. And our research is very generously supported by Department of Atomic Energy, the Intramural Grant, then India Alliance, Max Planck Society, Human Frontier Science Program, and ACRB. Thank you very much for your attention, and I'm happy to take whatever question you have.
We'll take questions one by one. Okay. First, you raise your hand. Wait, we get the mic. Everybody's there.
Why are you interested in fasting, if I may ask? See, I am not aware of any literature which connects the fasting and cancer from a physicist point of view. But there are literature where fasting is connected to the cancer through the metabolism point of view. Okay, so maybe you'd like to see those. And now, one thing you would like to explore is that how the metabolism and the mechanics interface. And this is one question we are definitely interested in, and possibly in collaborations with Ullah. Yeah, so that is the answer that I can give you. Yeah. Yes.
Why do you think cancer is so common? Because, or if you have just one cancer cell coming in, that trigger an point really requires diagnosis.
See, I'm not saying the fibrosis is really necessary. Okay, what I'm saying is that the having fibrosis helps. So, and this is what the data from the clinicians suggests, that there is a very high correlation between the fibrosis and the incidences of the cancer. Okay, for example, one of the things that people suspect, that one long-term effect of the COVID-19 infection and the people who who have been affected with COVID-19 and had this fibrosis in the lungs. We never know, maybe 5-10 years down the line, we may have some problem related to that. So this is a guess. And the reason this guess is that the fibrosis is associated with cancer, high incidences of cancer. So fibrosis is per se not necessary, but having fibrosis helps. Yeah. He is sitting just behind you. Yeah, so one of the problems is, I mean, when they discovered this, I tried looking at it, to be honest. But the problem is, these are all immunohistochemistry, this section data, right? And getting the nuclear morphology out of them from this section and the kind of detail they are present is little challenging. No, we haven't used any algorithm. Maybe we should do this. Yeah. Yeah, I get your point. Yeah. Sorry? Yeah, this is something we have to do at some point. We haven't. Yeah, so the reason, so we are focusing on the resistant cells mounting. Okay, so this is the reason our focus has been on the cell and the group of cells, because we are looking at the collective resistance that cells are mounting. But if you are asking whether these nuclei are really softer, so this. Now we have to use some other technique to measure the. Yeah, there are a few problems. One thing we are planning to do is basically use some sort of molecular tension sensor to measure that. Otherwise, see, I mean, one of the problems that I have against sort of the way of measuring the nuclear stiffness within the cell. So they bring the cantilever from the outside the cell, right? So when they're talking about the nuclear stiffness, they are also measuring the cytoplasmic stiffness plus the nuclear stiffness. So this is not the, and if you take the nucleus out of the cell, then the lot of properties are changing. And one of the things that he has found is that the caging of the nucleus that disappears. And this is something you cannot capture if you take the nucleus out of the cell. So we are planning to do this experiment, and for that reason, there is a small technical problem that I can tell you, but we'll solve this in another couple. Yeah, yeah. Yes. Hmm. Hmm. Hmm.
Before creation of the cancer, seeing the tissues of cells, whether you are able to identify that it's a chance for the creation of cancer.
That's an excellent question, and this is something I also ask myself. Okay, and if I give you answer that, I will focus on the prevention of cancer. So the initial stage of cancer, okay, to try to understand how the quality control in our tissue works, where it fails, and how we can make it better. So I will work in the initial stage of the cancer rather than the final stage of the cancer. And I don't know what is better, but it seems that people have been working on the final stages of this process called metastasis, whether the cells are taking the highway and then colonizing for some time. But this area where they're actually looking at the initial part of the cancer is very less studied. And this is what I feel like I need to understand. Okay? Yeah. Yes.
Would that also be a contributing factor? And if I compare epithelial tissue from my respiratory tract and my GI, would they usually stiffness?
Yeah, so that's a very good question. In principle, it should. But how it is, this is where one is to devise an experiment where this experiment are doing in the physiological setting, where the cells are experiencing. In fact, there are some experiments. So there is a group called Rakesh Jain, somewhere in between the MIT and okay. This is Broad Institute or this institute. So what they did, they took the cells, and then they applied some artificial pressure from the top, and then they saw that the cells they're not really putting pressure on the cells directly, but they are compressing the liquid. So the cells are cultured, you have the liquid on top, and from there you are putting some weight. And then if you put the weight, you will see that the cells kind of might start migrating. So this is one of the things which should tell you that what kind of forces, this sort of compressive forces or the extensile forces the tissue experience plays an important role. But how, this is something we need to understand better. See, one of the things is that so when I talk, when I talk about the cancer here, I was talking about the epithelial cancer of the epithelial tissue. So the stiffness ranges of the epithelial tissue that they don't vary too much. So when we are talking about those extreme range, like the 200 Pascal, in one end you have the gigapascal, you are talking about the bone tissue and you are talking about the brain tissue, right? So if you are sticking to, let's say, the epithelial tissue, then tissue to tissue stiffness variation is not that much. That's what I tell you. Okay, but there are of course differences. But whether that differences play any role, this is something we do not know yet. It is actually very hard to sort of pinpoint a specific factor across many things. It is all you can do as an experimentalist, you can change one factor, and this is your hope. Because if you change one factor, other factor will also change. This is the advantage with physicists. They have their nice model, they will change one parameter, and then they can study one parameter in isolation, that what is the effect. But as a biologist, and if you are doing experiment, the problem is that the main challenge is how do you change one parameter and then you get the effect in the output, right? And so that itself is a problem. And then if you compare like multiple tissues and so, which is a different architecture, which has probably different physiology and so, then the picture is more complex so that you cannot pin it down to one single factor. Yeah, I have no problem. Yeah, it's my pleasure.